Okay, so in a previous video I showed how I made this finite element model of a fracture fixation construct, how I modeled the geometry, the material, how I made the mesh so precise with hexagonal elements rather than tetrahedral, how I modeled the contact between the plate and the bone, and also between the screws and the bone. And this is what it produced. This is the stress distribution, the film measure stress distribution around the bone with this number of elements. This is the and deformed shape. Now the deformed shape is this one. To see a little bit of how that goes from undeformed to deformed. This is what happens. So you can see at the edges. Well, you can't see it too well here, but if I take off the implant, you can see very well here at the edges, at the last screws, there is a concentration of stress there. And in my thesis, the problem I'm dealing with is this, how to minimize this concentration of stress, right? So to show that a little bit better, I made some 2D plots. And the way to make the 2D plots, I'm going to show it just here once, is I made a path around this. I mean, here you can see that it's constant, the stress. So you expect a constant stress. So I didn't plot the stress there. I plotted the stress. Let me look at the undeformed shape. Put the stress along this. So it takes into account all these elements, right? So we expect already a peak here and a little bit of a peak here, but the maximum peaks will be in the sides. But if with a 2D plot, we can see it much better, right? So I did that. And for only the bone, I found these, right? So you can see, I can analyze it much better here in a 2D plot. You can see again this peak stress here at the edges, which has been noted that bones fracture, because of these peak stresses produced. I should also say again that the loading applied is pure bending at the edges, at the ends of the bone. You can see them the previous video to see exactly how I did that. But anyway, so this is the curve you get for the stress there, stress distribution. And you also see here a decrease in stress along the length of the bone. Many people refer to this as stress shielding because the bone effectively feels less stress due to the rigid plate on top. If you look at my thesis, and also a lot of researchers have showed that this is related to both the geometry of the implant and bone together, and the increase in Young's modulus. So it's the rigidity is often described by the Young's modulus times by the inertia of the construct, and this is effectively increased in this. Let me show again with the implant. In this region, right, there's a higher diameter, higher radius, and also the center, the center of inertia is also raised. And effectively, so inertia is raised, and the Young's modulus of this plate is higher than this, 110 gigapascals, whilst the Young's modulus of the cortical bone I'm modeling is 15 gigapascals, which is realistic. And so you get so there is that increase in rigidity, and it is often said that this is why there is a lack of stress and you can see it quite clearly here, right? So it's shielded, the bone is being shielded, and you can see nicely if we also plot. Then I did another one. If I then go and I removed, I removed the bone and I plotted the same thing, but for the plate only. Then we had this one before, And now this orange one, let me label them nicely. This orange one is for the plate. You can see that in the orange one there is an increase in stress rather than a decrease in stress, such in the bone. And then that's well, you can see that that's the stress that has been decreased in the bone. It's increased in the plate. So that's nice to see as well. Right. And I'm gonna leave it at that for now. Thank you for listening.